a story where you're being asked to find a 90, a 95, 80%, God, hopefully not, confidence interval. So I have a story. They ask 1,026 people. Excuse me, I'm looking for my calculator. Can't be too far. There it is. So they asked a sample of 1,026 people. How many of them, let's see, how many of them are vegetarians, right? And the sample came out that 121 of them were vegetarians. And so what we're going to do is we're going to use that information to estimate what percentage of Americans would be vegetarians. So basically, I've just made up a story, right? Now, you need to have as part of this question, don't you, what confidence interval you've been asked to find, agreed? So let's say 95%, right? So the question would be, find a 95% confidence interval based on this information. So far, so good. So I'm going to do it by hand because it's worth it. P hat plus or minus the magic Z score for 95% times. Can anybody remember the ugly square root guy that comes next?
Is it P hat times 1 minus P hat?
Which by the way is called Q in the textbook.
Oh yeah, Q hat.
No, but you're right. I call it 1 minus P hat as well. And underneath that, what do you divide by?
The number, the total number, right?
So in this case, it's going to be, let's get the calculator involved now. It's going to be 121 divided by 1,026. And I'm going to call that 0.118. We should be getting good at this. What's the magic Z score for 95%?
Is it 1.96?
It is. Square root of 0.118, which is P, 0.882, which is what 1 minus P is, all divided by 1,026. So I'm now going to go to my calculator and I'm going to go 1.96 multiplied by the square root of 0.118 times 0.882 divided by 1026. And I am looking at that guy. So it's 0.118, give or take 0.0. Whoa, that's going a bit weird. 0.0, if you round it off to 3 decimal places, are you okay with that number? That 0.0197 rounds off to 0.020, right? It's just a little bit weird looking. In interval notation, this is going to be 0.118, take away the margin of error. So that comes out to be, try that again, I didn't type in the right number, 118, take away 0.02, that's better. And that gets me 0.098. And if you go the other way, it's 0.138. And human beings would prefer 9.8% to 13.8%. And this guy here, if you're writing it down, you would probably call this 11.8% plus or minus a margin of error of 2%. Great. So there might have been a news story. Hey, new poll out. 11.8% of Americans are vegetarian, and the margin of error was plus or minus 2%. I hope that's the way they would phrase it. And then they might go on and they say, oh, 50 years ago, it was only 3%. So there's a lot more vegetarians today than there was in the past. And then they bring on a guy that tells you why being a vegetarian is so good for you, right? That's the kind of, imagine what the show would be like, right? That's the kind of things you would do. So these 95% confidence intervals are basically saying we're 95% confident the percentage of vegetarians in America is somewhere between 9.8 and 13.8%. That's quite a narrow band, isn't it? That's pretty close. It could be as low as 10% roughly. Could be as high as 14. That's quite a small window. And the main reason for that wasn't it to do with the sample size. 1,000's a good number, right? The Gallup poll number's 1,000 and change. Now, that same question with the same numbers is now going to be done on the calculator. And all I need for the calculator is to make sure that I hit start. And I go over to tests. And can anybody remember which guy I need to do?
A. 1 prop Z interval?
That's it is. And when I type this in, it says X. X is how many people said yes to being a vegetarian. N is the total number of people, which is 1,026. And isn't the confidence level 0.95? Now, in a lot of ways, isn't that so much easier to deal with than to do it by hand? But I think doing it by hand does help. Doesn't it give you a kind of feel for, it's not magic. I could do it this way. There's a calculator here that does it for me, so I'll probably end up doing it that way. They've rounded off a little bit, but would you agree these are the same numbers? Do you see this interval, and the one there is the same? They even tell me p hat, which I knew already. Right, the 1179 is 118. Now, if you choose, oops, I can't move it there. If you choose to do only on the calculator, don't they very often in the homework ask you for the margin of error? If you do it by hand, getting the margin of error is part of the process. But if all you know is 0.098 to 0.138, which is what I have, how can we get the margin of error? Just using the limits that we have here.
Subtract.
I hear subtract in 2 places, so I'll do that. And then do something else, right?
Then divide by.
By?
2.
2, yes. So it's not a biggie, right? And you understand why that works. If you can imagine this as a number line, and over here we have 0.098, and over here we have 0.138, and then we've got a guy in the middle. Don't you go a margin of error either side? So doesn't that mean that from there to there, is it not 2 E's worth, right? And so that's why the divide by 2 comes in, and if you subtract them, that's the length. So you take the length and half it, and that's why that works. And that would be your margin of error. Looking good? I'm going to take a quick scan at the questions here to see if there's anything here. Oh God, yeah. Me and this, I'm going to hopefully go one day. We go to conferences, at least used to go to conferences once a year. And one of the things that was kind of cool in a conference is that we got to meet a lot of the authors, because they're trying to get, colleges to buy their books, right? So we get to meet the authors. I think if I meet this author, we're not going to get on well together, because my conversation's going to revolve around of why on earth did you put 80% in as a confidence interval? It's a bad thing to do. And he might come up with an argument for it, but I'm not going to be convinced. And now I'm about to give you a second thing which I've just noticed. remember we talked about conditions to be able to use this process. And one of them is the sample size had to be large enough, and n times p, technically n times p hat, right, had to be bigger than 10, and n1 minus p had to be bigger than 10, right? Sure, I told you that, and if I didn't, I'm now telling you, right? You know what this book does? You have to go with their answer because you want the homework to be right, but it's 10. Trust me, it's 10. Go look at online, right? Just go online and say proportion test sample size or something, right? And you'll see this, right? While I'm at it, don't they do X bar plus 2.5 standard deviations mean it's an outlier? And what does the rest of the world do? X bar plus or minus 3 standard deviations. Right? They're more like nitpicky things, right? Or maybe it's just me and I'm Scotland, and I think Scotland did it right in America. Maybe this is an American thing. I doubt it. I think it's this guy in this textbook thing. But just in case you go and you say, but none of the answers have a 10 in it. I just noticed right now, none of the answers have a 10 in it. You have to do a 5. And that is what it is. Okay, I think for the last one of these, and I'll do it both ways again so you can get practice at saying it by hand, I'm going to have to move this over here so I can see you all. Do a thingy-bob, stretch it out. Right, I'm going to just ask a question. There's going to be 1, 2, 3, 4, 5, 10, 15, 20. Right, the sample size is going to be 25. Okay, so let's see, what can I ask? How many of you are fans of the Seahawks? Put the little happy hand wave at me thing. Thumbs up, 1. Anybody? 2. Me, I'm 3, 4, 5, 6. Okay, we got an answer. 6 out of 25. So Seahawks fans at Olympic College. So you lot are representing Olympic College students, and I would like to know what percentage of Olympic College students are Seahawks fans. So see what that guy looks like. 6 divided by 25, 24%. Let's do a 90% confidence interval, because that is part of the question. So it's going to be p hat, give or take, the magic z-score, times the square root p hat, and take away p hat over n. So 0.24, give or take. All right, I got it in front of me here. Magic z-score for 90%.
$1.645.
You nailed it. There you go. So I'm going to go and get the margin of error next. So 1.645 times the square root of 0.24 times 0.76 divided by 25 and 0.14. Let's just round it off to 14, right? Keep it simple. That is 24% plus or minus 14%. So somewhere between, it might be as low as 10% of OC students or Seahawks fans. It might be as high as 38%. We feel comfortable about that process now. It's very standard, isn't it? Once you've done enough of them, they all look the same up to a point. Great. Let's do it the other way. Do tests, go down to 0. Sorry, go down to A. Hit the guy. Only 6 of you out of 25 with a 0.90 and calculate. And 24%, check. Would you agree 0.0995 is darn close to 10%, right? And would you agree 3805 is basically 38%? So we know we got the right answer, right? Except in your homework, don't you have to type in, you know, the decimal version, not the percentage version?
And the,
right.
and
Sorry,
the,
Mary?
the interpretation for that interval of 10% and 38% would be that we are 90% confident that the true percentage of Seahawks fans out of Olympic college students is between 10% and 38%?
Yes.
Okay.
That was a nice short answer, yes. I know we've done a few of these, but the thing that I like about these is it's relatively simple, but at the same time, it's very powerful. You can make a prediction based on millions of people, right? You know, if your sample is a good, fair representation of the population, whatever that population is, this technique will give you really good, usable results. And there are a lot of, I can't remember the phrase, but I think it's called something like evidence-based decisions or something, which basically means if you're in business and you want to make a decision about something, then instead of just going with your gut, you actually collect data and you use that information to do your thing. So I'll try to off the top of my head. Let's suppose you're a cruise company and you're trying to decide when to start doing cruises again. Now, if you do them too early and not enough people actually book the cruise, then could you see that you could end up losing money out of it because the tickets you get doesn't cover the costs of the cruise? Secondly, people might get ill and that won't be a good thing either, right? Of course, if you wait too long, won't you miss the opportunity to make some money? Because right now you're making nothing, right? Your ships are just sitting somewhere. I'm assuming that you've paid off your crew. Maybe you haven't. That'd be nice if you haven't, but you're not getting any money, right? Because you're not cruising. And so you don't want to wait too late. So I guess the question they might have to know is, when should I start doing cruises? So they would go to a place like Gallup Poll, and you would say to Gallup Poll, right, are people ready to go cruises in February? So you'd get a sample and you say, would you go to a cruise this coming February? And then they'd get another group and would you come in March and would you come in April, right? Or they could ask them the sequence of questions, right? So they get the data all at once. And then couldn't you figure out a sweet point? Because, you know, right now, in fact, do you know at the height of the COVID thing, do you know there's some people who would say, heck, I'm 18, I can go on a cruise, not a problem. No, you shouldn't probably, right? But you imagine there are going to be some people. But isn't there going to be a sweet point where the cruise ship will say, yeah, March is good. A lot of people would say, I'm going to go on a cruise in March. And then they would start cruising at March, right? They put out adverts. Do you want to go to the Caribbean this March? Here's the prices. Get some people, start cruising. I love cruises, by the way, and I am going cruising in March. And if the COVID comes anywhere near me, I'm punching it in the face. Because me and it are not friends. But I've never let, I'm weird, I've never let. Do you know when 9/11 happened, which was a terrible time? I had booked a flight to go to Scotland, I think it was 2 months later. I went to Scotland. Didn't care. Flew there, not a problem. The airport that I arrive in is called Glasgow Airport. And Glasgow Airport, 2 weeks, I think, before I was due to fly into Scotland, got a terrorist attack. This guy, strange story. Don't know why he did it. I guess they do it because they do it. Was a doctor at a local hospital. He was actually well off. Wasn't a poor guy. No reason to do it. Anyway, he drove his car up and it was filled with big tanks of propane gas. And he set them and he basically set a bomb off to cause a fireball to kill as many people arriving at the front of the airport. Because you could drive right up to the front door of Glasgow Airport and walk right in. And so he parked there. And it never went off right, thank goodness. And the people he was trying to kill like 10 seconds before rushed into the vehicle and dragged him out, tried to save his life, but he was too badly burnt. Just interesting that people have that mindset. Anyway, they did that. And 2 weeks later, I flew into Glasgow Airport. And when I flew into Glasgow Airport, first time in my life I ever seen this, British cops with submachine guns all over the place. So I never let things like that bug me. To heck, if you let them bug you, they've won. So that's my attitude to everything. So don't know why I shared that. I guess it's because I'm homesick again. Anything about Scotland sets me off. Okay, are we good with proportions? Are we happy about what you do and how you do them? Right.
I was just wondering, for the exam, do you have a preference whether we use the formula by hand or the calculator?
Well, I'm not going to phrase this. If you get it correct, there won't be a problem. But if you get it wrong with the calculator, I can't see anything to give you partial credit. So I guess it's a gambling game. Do you feel lucky? If you feel that you're comfortable hitting the buttons, you could certainly do it that way. And if it's the right answer, I'm going to give you the points. You couldn't get the right answer by not doing it correctly. You get what I'm saying? You couldn't guess the right answer, right? So I know you must have done it correctly. But if you want, because maybe you make a mistake and you're just careless, as I am, you might want to write the working down, because then I can follow the process and, oh yeah, she wrote, whatever. She wrote 1.23 when she meant to write 1.32, that kind of thing. Or she did it to 3 decimal places, but the books, it wanted 4. All those things that can screw up an answer. So my advice would be to do it the long way. My advice in the homework, however, would probably do the short way, because doesn't the homework tell you the answer right away? So I don't know
Might
if
even be good to do it both ways to check your answer.
if you have the time, definitely, for sure. It's a time management thing, how quick. Some people take longer and therefore they might not have time, and I understand that. But if you could, that would probably be the ultimate best way of doing it. Even in the test, shouldn't you do it both ways? Yeah, if that's what you meant, I agree with you even more. Right. So if you could wait a second. I just had a bad joke come to me, so I'm going to have to share it. It's a Polish joke. Are you ready? Did you hear about the Polish kamikaze pilot? He flew 14 successful missions. I think Zoe liked that one. Zoe, why on earth did you like that one? It was just,
I don't know.
it was just that dumb, it was funny. Jenny, you look like you liked that one.
Yeah, it was pretty silly.
Silly is, yeah, I like silly. The reason I'm taking a little bit longer is I want to, if I can damn find the thing. Okay. I couldn't find what I was looking for. Let me try one last time. Basically, we're looking at differences in means and differences in proportions. But there's a thing, I know it's somewhere. But where the heck is it? Okay. You know what's going to happen? Once this lesson's finished, I'm going to find the thing I'm talking about. Yeah, it's just guaranteed. Right? But until then, I'll just get on with what we were going to do. And I should be able to do. Okay. Oh, anybody got a question in the chat? Okay, let's see if we can share it. Oh, we may have been sharing it all the time. We'll be sharing this all the time. I don't know what you were saying. Are you now looking at whiteboard? Okay. We are going to look at the differences in means. So we've looked at an estimate for one mean, a single sample, and we're looking at the heights. So I want you to imagine that we are looking at two different samples. So let's suppose that we were looking at the weights of, let's try and spell that right. The weights of lions. Right, so you're an anthropologist, not an anthropologist, a zoologist, right? And you're interested in lions. And one of the things you might be interested in working with these lions is there a difference between their weights? Right? Are males typically heavier or lighter than females, right? Imagine that kind of question. So you're interested in the difference between two distinct groups. So you go and you get a sample of, I don't know, maybe zoos or out in the wild, whatever, and you get 100 males. And I don't know what a lion weighs, but can we pretend I do? And it's 150. And I'm going to call this N1 and X1. And let's suppose, for some reason, I even know the standard deviation of male lions. Now, on the other side, I collect, for some reason, there's more females. Actually, that's true in the wild. Do you know there's more females than males? There's only one head male lion and maybe a few younger ones, which will be his children. The rest of the males get kind of booted out of the herd, and a single male lion on its own has a hard life, because if you're going hunting for antelope, it's much better if there's 10 lions all charging around, right? Somebody's going to get one of them, right? But if you're one lion on its own, actually what they do is they get together as a pack of male lions, right? They kind of hang out, but even that. So back to the story. I think, and I'm only guessing here, that females are lighter than male lions. Let's say that's true. And let's say that I also somehow managed to know what the standard deviation of them are. Now, mu1 and mu2 would represent the population mean for male lions, right? And the population mean for female lions. And I would like to estimate mu1 take away mu2.
Just a quick thing, the sigma for females
Oops.
is sigma 2, right?
Yeah,
Okay.
correct. You all caught that deliberate mistake, right? So how do we come up with an estimate for this? Would it seem reasonable that you would have that? And then wouldn't you have plus or minus your margin of error? Agreed? And there would be a formula for this margin of error. So far, so good. And it's going to be x1 bar, x2 bar, plus or minus. Got this little guy. Whoops. What the heck? I've moved the wrong thing. Never mind. The margin of error is ZC, right? That's going to be the magic Z score for 90, 95, 99. This is a new guy. We've never seen this guy before. Right, you see this fellow here? Right, if I cover this term up, won't that eventually just become sigma over root n? Right. Can you imagine I wrote that down? Sigma 1 squared over n. Couldn't that become sigma squared over n? Oops, that. Which then became sigma over root n. Do you recognize it now? And if I did it to this guy, wouldn't you get the same? So does that sort of a kind of make sense how this weird square root thing appears? It's basically the standard deviation of the males joined together in some weird way with the standard deviation of the females, right? That's what these two things are. And you put this package together and you will have your estimate of the difference between them. Now, if this number happens to be bigger than 0, does it not mean there's evidence that males are bigger than females? Suppose this number ends up being negative. Is it not now evidence that males are lighter than females? And that's really the only two choices, right? I guess the third choice is they're both about the same, right? But let's see what we have in our storyline. It's going to be 150. No, it's, yes. Take away 130, plus or minus. What kind of confidence interval do you want to do in this difference? And you're not allowed 80% because I hate that one. But apart from that one, which one do you want?
99.
Okay, so that's going to be a 2.58, right? That's 99. Square root of 20 squared divided by 100 and 15 squared divided by 200. See, sigma squared over n1, 20 squared over 100, sigma 2 squared over n2, 15 squared over 200. Are you comfortable about where all these numbers are coming from? Right, they're all coming from here. And I don't know why I did that. Shouldn't I have called it 20? 20. Right, it's going to be plus or minus this horrible mess. So here goes. on my calculator, 2.58 times the square root of 20 squared divided by 100 plus 15 squared divided by 200. And I'm looking at 5.84. Does that look good? Got a nod, I'm using it. Isn't that 5.84 called the margin of error? Now let's see what that boils down to. That boils down to 14.16 and 25.84. So we are 99% confident that the difference in male and female lines is in this range. Are all these numbers positive? Yes. Agreed, they're all positive. Can I now say there is strong evidence? I would call 99% strong, right? There is strong evidence that male lines are heavier than female lines. I could probably get a little bit more than that. Not only is there strong evidence that male lines are heavier than female lines, wouldn't you say that there's strong evidence that male lines are 14 pounds heavier than female lines? And you might say, why 14 pounds? Do you see that number there? Isn't that at the extreme low value of the difference? So you can tell the difference between them, and you can also sometimes, if you use this number, put a value to it. So I can say male lines, yeah, in general, they're heavier than female. In fact, in general, they're about 14 pounds heavier. Now, that does not mean that every single female line is lighter than every single male line. Can't you just get some small, skinny male lines and some big, fat female lines? What we're saying is that the average weight of a male line is more than the average weight of a female line, right? So maybe it sounds the same, but that is a slightly different nuance, isn't it, to what that is telling us. Wouldn't it be nice if we could do all of this on the calculator? Maybe even more so than what we've done in the other situations. Agreed? So,
Professor, I have a question.
Sure.
Does that interval, does it mean we're 99% confident that the difference in means is in that interval?
Yes.
Okay.
I'm getting some really short answers today, which I like, because what it's really telling me is you kind of knew it, but you just wanted confirmation that you knew it, right? Because you basically said the right things, and I said, yes, you're right. So let me see where this little guy is. Okay. It's less hassle for me if I put the calculator here and do it than all that in and out carry on. For most of you, can you see this guy? Right. So I kind of promised you that you could do this on the calculator. So now I'm going to have to prove to you that you can, right? Any guesses where it might be hiding?
Stat?
And if it wasn't in stats, where's the only other place it could be hiding?
Distribution?
And it is. I hit the wrong buttons there. Let me check that. I take it back. I'm wrong. It was in stats. Hey, if it wasn't one, it had to be the other. My apologies. Okay. Now, the guy that we are going to be using here, I think it's this one. Let me check this before I commit myself to it. Uh-oh. Claire. It's here. Right, now I've forgotten where I found it. It's under tests. Right. That's a test. Want an interval. There we go. Right, as if I never told you, hit start. There's so many ones that look just like it. Tests. We're going to do tests. And then we're going to scroll down to 2 sample Z intervals. 2 samples. I couldn't figure out for the life of me what the name of it was, because there's 2 Z test and 2 this and 2 that. But 2 sample Z interval, number 9. And we're going to use the stat mode. And I'm going to go and type in the data. Sigma 1 was 20. Sigma 2 was 15. X bar was 150, that's the male lines. There was 100 in the sample. X2 was, the mean of X2 was 130. The sample size was 200. Confidence level was 99. And then calculate. And I want to see, whoops, these guys, right? Would you agree that is 14.16 and change and 25.84? Okay, there's a little bit of rounding off there. That could have been me not being careful about my rounding off. But would you agree it's the answer, right? So you can do it by hand, or you can now do it by using the calculator. I should have added, so I'm now going to do it. This is the difference in means. Sigma known. You know sigma, right? In fact, you know sigmas. Sigma's known. Right. Let's do another one, but just do the calculator version because it's a lot quicker. Let's suppose that we have 2 distinct groups, and we are going to have someone's trying again. We're going to have Scotland, and we're going to have England, and we are going to measure in their average heights. So we got 500 Scottish people, and their average height was 65 inches, and that the standard deviation for Scottish people was 5. And we got 1,000 English people, and the mean of that sample was 66, and that the standard deviation was 2. And we are interested in estimating the difference. And we'll do this one with a 90% confidence interval. Now, superficially, doesn't it look like the English are on average taller than Scottish people? But they're very close, and couldn't that just happen by luck, by just a sample happen to generate that? And so when we create this confidence interval, if that confidence interval has nothing but negative numbers in it, then doesn't that mean that the English are in fact taller than the Scottish? Because a negative difference means the second guy is bigger than the first, right? If my interval has positive and negative numbers in it, so it's negative, 1.1 to positive 2.2, that kind of thing, then isn't that basically saying that there is no evidence that English or Scottish are taller or smaller than the others, right? There's at least not in this particular sample set. So that's kind of where we're heading. And the cool news is that hopefully, I hope you can remember where the heck it is, because I jumped in and out about 4 windows. I do know where it is because I now do remember. Does anyone want to tell me where I go next?
You go to test and then you go all the way down to 9, I believe.
You are so good. After only seeing it once. Right, so boom. Right, now we're still on stats, right? That's cool. So in this case here, that's 5. And then it's 2. And then Scots guys are 51, and that was a sample of 500 that gave us that. The English came out at 66 inches, but that was a much bigger sample. We're going to do a 0.90 confidence interval, and then we're going to hit calculate. And the answer that we're getting is negative 1.382 and negative 0.6178. Now that is actually correct. Do you know that negative numbers like negative 1.3 are smaller than negative 0.6? So if you think that looks back to front, it's not. If I draw a little number line here, can you imagine this is 0? And round about here is negative 0.6178. And then a little bit further on is negative 1.382. Can you see that the interval that represents the difference between them is from here to here? Aren't all those numbers negative? Every single one of them. And if they are negative, doesn't that mean that mu1 take away mu2 is negative? And if you do a little bit of math, it's not much. Oops. Negative. Right? If you do a very simple piece of math, can't you just prove that? So do you see why negative means M2 is bigger than M1? Why English are taller than Scottish people? Great. So I would be able to say there is evidence. You can decide if you think the word strong belongs there or not yourself. There is evidence how does I phrase that? To prove that the English are taller on average, right? Than Scottish people. Could I get a little bit more mileage out of it? Right, if you look at these two numbers, isn't the worst case scenario, right? The worst case scenario would be here, right? Isn't that 0.6 of an inch? So couldn't I put in something like 0.6, or if I wanted to be a half an inch taller on average? There's evidence to prove not only are the English taller, but they're about 0.6 of an inch taller. So choose one of the numbers on the interval, the less extreme. Because these are negative, this side is the less extreme. When it was the line one, didn't we pick the other end, right? The smaller end was on the left side, and that was the less extreme. And so you can not only say that one group is bigger or smaller on average than the second group, can't you also put a value to how much bigger or how much smaller? Suppose we did this question, but the interval was negative 1.2 to positive 0.2, right? Because that could have happened, right? wouldn't that not be evidence that English are taller or smaller than the Scottish? And isn't it possible, at least, that Scottish people are 0.1 or 0.2 inches taller than English? It could be that the English are 1 inch taller than the Scottish. All of these numbers are just as likely as any other number, right? All of those differences are equally likely. And so there's no evidence to confirm one way or the other.
So could you confidently say that that's like a 50, like half 50-50 chance that they could be either one, basically?
No, unfortunately. All you can really say, because there's not enough detail in the sample to honestly say that. Couldn't I just get a really bad sample of Scottish and a really good sample of English? There's no way of actually figuring that out. All we can say for sure is that interval means we can't say anything about who's bigger or who's smaller.
Okay.
And we can't even say 50-50. And I know there are a lot more negatives than there are positives, so we can't even like distribute it and say 80% chance English, 20% chance it's Scottish. The reason for that is there is only one answer, right? The population has one number for mu1 and the population has another number for mu2. Isn't the difference a single number? So theoretically, the answer is either 100%, you got it, or 0, you didn't. So you can't really qualify it with a percentage. But it is a kind of, are you happy with this new guy in town? How you find a confidence interval for the difference between two means when sigma is known, right? Now, if sigma was known, but we gave you data, right? So we told you sigma was 5, and here are some Scots guys' heights. Right? Wouldn't you have to calculate X bar and N on your own and plug it in, right? Or you could go back to the calculator and you would have to do something like this. You'd go into edit. And you'd put in the Scottish guys, 65, 63, 61, nice tall guy, 69, finishing with 60, right? And then you'd go and you get some sample of English, right? You asked 8 Englishmen, you found their height, right? And you got 56 and 64 and 65 and 62 and 69, and maybe you got a few more English, right? You'd put the data in. Now you're still finding the difference in the means, right? A confidence interval for the difference of the means, but now we're doing it through data. So when I hit the start button, this is the only major difference. When we go down to the bottom, number 9, and we hit enter, do you notice I move over to the data side? Because my numbers are not X bar, right? It's the data I'm going to use. And mu1 was 5, that's good. Mu2 was 2. Isn't L1 where I put all the Scottish guys? Isn't L2 where I put all the English guys? These guys are always 1. And there's my 0.9. Now this is different data sets, so don't expect the same numbers, right? I have no idea because I kind of randomly chucked in heights here. Let's find out what the difference between Scottish and English people are from just some samples that we wrote the numbers down for. And the answer comes out to be negative 0.67 to positive 1.05. In other words, there's no evidence there to prove either is bigger or smaller. You see, there's positive and negative numbers in that. We could get lucky, couldn't we? And the Scottish could be, what, an inch taller than the English. I guess if I was a gambling person, isn't it more likely that the English are taller by about 6 inches or some number like that?
Can I ask a question about that?
Sure.
So if you have both positive and negative numbers in that range, then you can't prove it?
Correct.
Okay. But if you have both negative, then you can.
Or both positives.
Or both positive. Okay.
See, if they're both positives, that means Scots guys are taller than English. If they're both negatives, that means, depends how you want to phrase it. Scottish guys are smaller than English, right? You could phrase it that way. Or English guys are taller than Scottish, which is the same information, right? You're just phrasing it differently. But if you get one of each, you can't prove it. You can give an interval, which we can, and that's pretty much what they're going to ask. I think in the homework, they're probably going to say lower interval, higher interval, or something like that. So in each box, you put the numbers. There is a margin of error going on here. Right? There's a margin of error. Can't we get the margin of error the same way that we always did if you know the interval? Can't you just subtract the 2 and divide by 2? I don't know what that number is. By the way, do you know sometimes that number might be negative, but remember, is it margin of error plus or minus, whatever it is? So I'm looking at this number here. It looks like 1.05 take away 6.71. So 1.05 subtract bracket negative 6.7. And that's that guy. And then you divide it by 2. And so the answer is what, about a margin of error plus or minus 3.8 inches, 3.9 inches. Are we okay now with estimating the difference between two means when sigma is known? Do you want to see another example of that?
Maybe one more.
One more, okay. I think for the next one then, maybe I should do one where it's data rather than X bars, right? So let's suppose that you were doing an experiment and you wanted to know, yeah, they do this in psychology. Do you know sometimes they do things in psychology to try and see whether or not there's a difference between things. So let's suppose that they were looking at, does coffee help you memorize things, right? Okay. So what they do is they give you a test, and the test is very often very boring things, but memory-based things. Like, here is a set of 12 digits. How many can you memorize, right? How many do you get right? And so they asked, let's make it 10 digits because it makes my life easier. And group A came in and they hadn't any coffee yet. And you gave them the thing, and these are the numbers of how many they got right. Okay, so you give them a memory test, and this person got 7 out of 10 right. This guy here hasn't. This guy's got my memory right. He's got 2 out of 10 right. This is what they got. And this sample happened to be 1, 2, 3, 4, 5, 6, 7. A sample size is 7. And in these questions, you just have to know what sigma is. So let's suppose that this guy has done this enough times to know that the sigma is 2. And then you go and you grab the same group of people, right? And you give them some coffee. And they drink the coffee and they do the same kind of memory thing. And you get 8, 7, 6, 5, 6, 3, 4. Now, have you noticed that some people did better and a couple actually did worse? You know, in this particular situation, that's that guy, right? You know, if you use an experiment, isn't it a good idea to use the same people that you used without coffee and then the same people after they get coffee, right? So you're kind of comparing like with like. So we got these set there. And I guess the question would be, I'd like to estimate the difference between them, right? I'd like to find what mu1 take away mu2 is. Now, if all these numbers are positive, doesn't that mean that people who didn't take coffee tended to do better at memory. If all these numbers are negative, right, if the interval ends up being negative, doesn't that mean that taking coffee helps you memorize things, right? You're better at memorizing. And if you get a bit of each, doesn't that probably mean that coffee doesn't help one way or the other as far as memorizing things? So I don't know what we're going to get, but I know we're going to do it in a calculator. These two samples share the same sample size and share the same standard deviation. That's not necessary, it just happens to be in my story. Would you agree some stories that can be true? So I'm going to hit start button. I'm going to go over to tests and I'm going to go to number 9. I'm going to hit it. And you see I'm going to be in data and I forgot to do something. Then I forget to put the data in L1 and L2 because if I use it right now, wouldn't I be using the Height of Scotsman data? So rewind, hit starts, go edit, go over to this side and just get rid of everybody. Then go over here and get rid of everybody. And now I can start with the first one. So 7, 9, 5, 4, 3, 2, and 5. And then 8, 7, 6, 5, 6, 3, and 4. Right, now my data's in. I'll go back and do the stats. I'll go over to tests and I'll go down to number 9. And I'll do a 2 sample Z interval. And I'll hit enter. And I've got data. And I'm going to make this guy 7. No, I'm not. I'm going to make this guy 2. I'm going to make this guy 2. Keep them the same, keep them the same. I forgot a confidence interval here. What do you want?
95.
Okay, 95 it is. And calculate. And the answer is negative 2.7 and positive 1.5. I'm just going to call it different, right? There's no evidence that one is better or worse than the other because don't you have negative and positive numbers here? So right now, I guess what I've done is spent some money and some time. Nobody's ever going to write a paper in the Psychology Journal, whatever they're called. I did an experiment on coffee and memory, and my conclusion is that I didn't find any evidence that there was a difference between the two. Now, not finding evidence is not the same as saying that coffee doesn't affect memory. It's just a reflection of I never found any evidence. But it's not a surprise. My samples are tiny. Suppose I got a grant off the government, and believe it or not, the government will give you grants for some really stupid things. The government will give grants for people to find the number and average weight of the three-toed sloth or frog in Kansas. People get paid money to do stuff like that, right? I wish it was me, but that's a different story. So when you'd maybe do 500 people, right, get a decent sample. And I'm just going to pretend that I did that. And I went through the same process, but with 500 people. They'd done the memory test, and then 500 people take coffee and do the test. And I came up with the following numbers. So the difference between the two groups is definitely negative. Agreed? And does it not mean that this is true? So would it not be good evidence that taking coffee does in fact improve memory? And then you could, this is made up, right? Then you go and you publish it, and people who are interested in that, if it was true, wouldn't teachers say to their students, at least the ones that are of age, look, the test is coming up tomorrow. There's good evidence that you should drink coffee because it'll help you remember stuff. And off you go. You're getting a bit old. Your memory ain't quite as good as it used to be. Why don't you drink coffee now as one of your main drinks? Because there's evidence to prove that that actually helps your memory. You see how these kind of pieces of information, if that was true, would be out there. Now, I can tell you why I don't believe that that is true, and it's not that I've got anything against coffee. But see, if it was true, wouldn't coffee companies be advertising the heck out of that fact? I mean, don't coffee or any company that's selling stuff, don't they want to find good things about what their stuff is? Hey, this stuff not only makes you, not fall asleep at work, right? But it helps your memory. And do you know those ridiculously small drinks that are just that are pure caffeine? Don't they sell them under the, well, if you take these, at least you'll be active during your work hours? Right. So I'm not sure if they have proved that or they've just did that as an unverified claim. It could well be true, because I do know that doesn't caffeine, some of you are probably even using it right now, doesn't it get your, I don't know what you call it, your awake level higher, your energy level higher? There's also a drawback to caffeine, isn't there? Which is the crash at the end. And I'm not sure it's good for your body to do that to it anyway, so I never drink coffee. But then again, I drink beer, which is definitely not good for my body. So I really shouldn't talk about people drinking coffee, should I? Are we good with that, to how to approach this question then? So now we have a new guy in town. We can find the difference in means when sigmas is known. So now I'm going to find the difference in means when sigmas are not known, which is very, very similar to what we did a way back. Didn't we find a single mean with, right, finding a confidence interval for a single mean when sigma was known, and then we found the interval for a single mean when sigma was unknown. Remember we did that way back in, was it 7172, whatever, right, way back, we did that. Can you see that the difference between two means has got a similar kind of flavor to it, right? This is how you do it when sigma is known, and we showed you it by hand and we showed you it by calculator. When you do not know sigma, all you basically have is two sets of data. You still want to compare the means, right? But you have to do it in a different way. So here is sample X1, and then I'm going to do sample X2. And in sample X1, you have 3, 5, 2, 5, 1, 0, 1. And in sample X2, you have 5, 3, 6, 7, 1, 0, 8. That's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Just want different sample sizes. Now, N1 is 7, and sample size N2 is 8. And let's just suppose that group 1 is America, And group 2 is Scotland. And we have collected couples and how many children they have. So in America, this family had 3 children, they had none, these 2 had 1, and so on. And we did the same in the Scottish family, right? This family had 5 children, this had 7, this had 1, this had none, and so on. And it's the same question. We want to estimate the difference. But in this case, you're not told sigma, right? Sigma is unknown. You're just told some samples. And from that, we're still going to be able to estimate it. If you remember back when we did this, wasn't this a student t distribution? And theoretically, at least, you could do it by hand, but nobody ever would, because you have to go to the back of the book to find the magic t-score for each sample size. Can you trust me, if you had to do it with 2 groups, you would be half an hour just getting the stuff. It is really not physically possible. And anyway, nobody would do it by hand anyway, I would suggest. We can do it by calculator. So first thing I'm going to do, only this time I've remembered, is I'm going to take the data and plug it in. So let's see what I've got. L1. So this is American families. There was a 3, there was a 5, and there was a 2, there's a 5, there's a 1, there's a 0, and then there was a 1. Then you move over to the Scottish data, and there was 5 in that family, 3, 6, 7, 1, 0, 8, 7. Right. That was pretty straightforward, right? It doesn't take too long. Okay, you're probably going to get bigger data samples, right? Can you imagine you're going to get 20 numbers maybe occasionally in the first column and maybe 15 numbers in the second, but not a biggie. Now, somewhere there's going to be a interval, right, that does this guy. It's stats. It's under tests. And as I scroll down here, do you see a guy called 0? And does he have a name that kind of tells you that's the right guy? It's a 2-sample t interval. Z is what you use if you know the standard deviation. T is what you have to use if you don't. See how that's going to work? A 2-sample t interval, right? Then I'm going to hit enter. And it's going to tell me what do I want? Statistics or data? I'm going to do data. L1 is fine, great. L2 is fine, that guy is fine, that guy's fine. Okay, let's do a 90% because I want to. Here's a question. Pulled or not pulled? You weren't expecting that, were you? Came out of the blue. This is what it means. If you do not know the standard deviation, but you can assume that they're probably the same number, just the same number that I don't know, then you will use the pooled. You'll say yes. Is there any real evidence that I know that the American standard deviation for family sizes and the Scottish one are the same? Is there any assumption that would be reasonable to say they're probably the same? I don't think so, right? Now, let's suppose, just for argument's sake, that we picked 2 different states in America, right? Washington and Alaska. I might argue there that although I don't know the standard deviation, since they're all Americans, it's probably going to be the same sigma, right? That would be my argument, in which case I'd say yes. Now, occasionally you get it wrong. Maybe you say yes and you shouldn't. And it's actually not going to make a heck of a difference. The 2 intervals are very similar, right? So it probably wouldn't matter too much. But if you don't know, or you can't think that they're the same, play safe and say no, right? Just play safe. If you don't know, you can't think of why they might be the same, you're probably right, just ignore it. Now, if I scroll down, I can now hit calculate. Now, did you notice how long it took the calculator to do that? Can I tell you one of the reasons it took so long is that if you had to do this by hand, it is horrendously messy, right? The formula is ridiculously ugly and fraught with danger. And now the only thing that I really care about is that the interval, oh, that was so close, wasn't it? Negative 4.5 and positive 0.1. So basically, I can tell you that my estimated difference between the mean of family sizes in America to Scotland is somewhere between negative 4.5 and 0.1. Can we just pretend, because I thought I'd put in enough numbers to make it happen, can we pretend that we got that? Right, pretend that was my interval. Would you agree these are all negative? Right, all negative. So that would be mu1 take away mu2 is negative. Won't that mean that Scottish families are probably, there's evidence then that Scottish families are larger than English families?
I missed which test you actually ended up on.
Let's show you that one. You go over to tests, you scroll down, and it's, yes, it's right, it's 0. It's right under, they tend to put them together. So it's right under the Z interval one, right? 2 sample, because there's 2 samples, right? Z interval means you know the standard deviation. T interval means that you don't. And that little pooled yes, no thing is just, do you believe that the 2 standard deviations, even although you don't know what they are, there's good reason to believe that they're the same, in which case you hit the yes button. And if you think that they're probably not the same, you hit the no button. The formulas are slightly different in each situation. That's why they ask you the question. And the numerical answers are very similar. So I am going to go back and do that same question again, but I'm going to change my answer from no to yes. So I got the data. That guy's good, that guy's good, that guy's good, that guy's good. And I'm going to say yes. And then I'm going to scroll down to calculate. And in this case, the answer is now negative 4.5 to positive 0.2. Do you see that they're darn close to being the same answer? So it's not, you know, if you were doing this, you know, and going to do a paper on it, or you were going to a conference somewhere and you're going to tell people at this conference whatever your evidence is, can you see that it doesn't matter too much? Won't you come up with pretty much the same conclusion? Which in both cases is there is no evidence that they're different.
On exams and homework, though, if we select
I
the wrong
would
level-
err on the side of no,
Okay.
unless the question says, oh, and their standard deviations are the same, right? If they told you it was, I think that would be. Because it is kind of hard. It's hard for anybody to really judge, are those standard deviations the same or not? Who knows? I mean, maybe American and Scottish standard deviations are the same. I don't know. It's kind of hard to put your finger on it. You might be able to get away with some circumstances might be more likely to be a yes. You know, I think Kansas and Alaska are probably got the same standard deviations, right? Because they're both American states. Whereas Japan and China probably don't, right? Boys and girls probably don't. You know, boys and girls, or males and females, aren't they very often quite different from each other in all sorts of things? And their standard deviations could also be quite different. Right? That would be my guesstimate. And if I choose wrongly, it won't be a fundamental disaster to my conclusion, because I'm probably going to conclude the same thing in both situations, aren't I? So it won't be I don't think it would be too significant. I need to think of one more example for today, because the cool news is that we've actually finished for this week, which means tomorrow I can get a head start. We'll do the section, but we won't put it in the homework. But maybe if you want to, I'll put it out there in case you want to get ahead of the game. That's fine. But I want to do one more example of this. Oh no, I get a better idea. I will do some more of this in a little while, but I think it would be more useful if I show you what the homework questions look like. Because very often I find out when I do that, that I didn't cover something. So where the heck are we? Gotcha. Okay, right. I'll go out and in and show you it now. It took me a little while to figure out. Anything in chat I should know about? Oh, somebody's talking about coffee. Let's go in here and oh, sassafrasin. I can't find the thing I want to find. There we go. It is here. We are all looking at homework from 7.4. Nod, good. Okay. The first one are just about, bigger than less than, and I worry about that later. Let's see what this one is. Okay, this guy here is 2 samples of data, and you're going to estimate the means. What you're going to have to do here is this, nowhere in that storyline, and there's a lot of storyline in here, but nowhere in this storyline do they tell me what sigma is. So does it not qualify as a sigma unknown? So can you imagine you'd have to type all of that into L1 and all of these 16 numbers into L2. And when you do your answer, you get these numbers as well as the interval, right? So I don't know if you noticed when I had it on the screen, I've got mine here right now. Not only did it tell me the interval, it told me x1, x2, sx1, and sx2. So you know that that's x1, that's sx1, that's x2 bar, and that's x2 bar. So all these numbers, you get them there, right? So that I didn't cover, but it was obvious that it was. Now, in this interval here, it's -90 to 107. Explain what the confidence interval means in the context of this problem. Because the interval contains both positive and negative numbers, we cannot say that one region is more interesting than the other. So evidently this is a story about how interesting you found 2 different places. And why did it use the student T thing instead of the Z thing? Wasn't it because you didn't know the sigmas? So that's what that was about. Now, I think this is basically some more data about phosphorus. This is revenue. Every single one of these right now is the T distribution, right? The 2 interval T. It's 2 interval T. We haven't done that yet. We haven't done the P's. I take that back. We haven't done the P's. Here's one. In this question here, question 11, do you notice that they've told us the sigmas? So can't I do the 2 Z interval version rather than the 2 T interval version? And P's, okay. T's, scrolling through T's. Right. We have not finished. I take it back. So I will tell you what we have still to do. And I guess I didn't realize it until I saw the questions. We haven't found how to find estimating the difference between two proportions. In other words, P1, take away P2. Right, haven't we done estimating P1, right? Wasn't, we just finished that, right? P1 hat, the magic number and so on. So we have two groups, A and B. And A is statistics people and B is football players.
Can you show us your white screen?
You would like to see that, I don't blame you. Okay. So we collected some samples of the IQs of statisticians and football players, right? People who take stats and people who play football. And the statistician peoples had IQs that look like this. One, two, three, four, five, six. And football players had IQs that look like this. That's the quarterback, because they tend to be quite bright. 1, 2, 3, 4, 5, 6. No particular reason why the samples need to be the same. Right? There's just no particular reason. Okay. Then wouldn't it be nice to estimate this fella? Okay. Now, if my difference, and I'm not sure I'm going to have time today to actually get done with it, but can we pretend I calculated, oh, shooting space. These are not proportions. I'm changing my story because my brain is still on means. I apologize. Okay. We asked 100 stats students, do they watch sports a lot, right? And the answer we got was 52 out of 100 said they watch sports regularly, or at least they did in the past. And we asked some football players, and we had 200 in that sample, right? And 180 of them said that they watch sports a lot. So evidently 10% of them have had their head hit too often, so they don't watch anything. I can't insult football players if there's not at least one of you here that is a football player. Oh, Doris is okay with that, okay. Why don't you, why should I be insulting football players, Doris?
I think it's funny. My brother plays football.
Okay, so you just like giving him a dig. Is your brother playing one of the positions where you need to be intelligent, or does he play that position where me grab crunch guy? That's
Yeah,
all.
plays. He's 6'5" and 17.
So he's the guy that just grabs people and crunches them.
Yeah.
So not a great deal of brain power is required for that process. She's not going with that one. Okay. Yeah, okay. We got it. Okay, so we want to put this together. So P1 hat is 52%, right? And P2 hat is, in this case, 90%. I think there's very strong evidence, would you agree, that the difference between these two, so basically P1 take away P2, that's what we're going to estimate. Would you agree that it's probably going to come out as a negative interval? Which means that football players watch sports regularly, more often than statistics students do. That's what I would expect. So, no, we don't have time. When you come in tomorrow, and that's good because it means I can do this with plenty of time to spare. We'll look at the formula for it and we'll do it by hand because it can be done by hand. And then we'll show you how to do it by calculator. So I can kind of remember this question because I know I'll throw this piece of paper away. Can someone remember the key data? So that when we come back tomorrow, that's where I'll start off from. Because with my life and the number of classes I teach and the fact that I don't drink coffee and have no memory, as a classic example of what I just did today, I totally spaced out the fact that we haven't done the difference between two proportions. And it should have been obvious, right? You do a mean, you do a proportion. You do a difference between two means, you should do a difference between two proportions, right? They kind of follow, right? You would expect that. But not in my brain. I just said, oh, great. It looks like we've done them all. Any questions before we go for today?
I have a question. Back to the original formula for the differences in means. You had a piece of paper where you're explaining the sigmas over n. And
Yes.
I think I got it. I think I was just confused
Okay.
by one of the things that you wrote, and I'll show you,
Right.
or I'll
But
tell
I got
you.
it. I'm pretty good. I think I know it.
Okay.
This was the formula that we use. And then there's a magic z-score out there. But the magic z-score's always been there, right?
Mhm.
Right. So what I was saying is, if you just isolate one piece of this, and then you split it into two separate square roots, the square root of sigma squared just comes out as sigma over that. And isn't that very like the formula that you used when it was only one sample? Right?
I guess I'm a bit rusty on my algebra because I forgot that a square root of one number of
Something
the other
square-
equals a square root
it's-
of that. Yeah.
Right? The square root of a fraction can be split into two separate
Okay.
square roots, and the square root of something squared cancels out and you just get the thing.
Okay.
So the square root of 10 squared is 10. Right. Now, if you do it with the other one, can you see that that ends up doing something very similar? So this here is how you group together two separate samples and combine them to get a kind of standard deviation for everybody, right? The whole process. So I was just really trying to say that this formula isn't, you know, there is a reason behind why it is the formula it is, right? There's a kind of algebra reason why it looks the way it does, right? And that's really all I was trying to get to. Now, by the way, you're not allowed to separate that into two separate pieces because there's a plus in the middle, and that's not allowed. But that's what I was doing. I hope it helped rather than confused you, but that's essentially all I was trying to do. Any other questions? Emily, I'm going to ask you a question then. Are you ready? Do you have any family who play football?
No, I don't.
Do you know anybody who plays football?
Yeah.
Am I being very nasty in my stereotype of football players?
No. I think it's accurate.
Well, one of the jobs I'm not meant to do is to make my students think like I do. In fact, if you end up thinking like I do, I have failed. What I want you to end up, especially in statistics, is to think in a skeptical way. That doesn't mean disbelieve everything. It just means be aware of how things could be twisted in a way to make you believe something that may or may not be true. And that's what my job should be. So being skeptical is good, but believing everything that I believe is not good, right? So you are